So we're going to now talk about how you might go about deriving numerical methods. And we're going to look at two classes of methods, one of which are one-step methods versus multi-step methods. And I'll explain what that distinction is. Okay, so if you're given a trajectory, a discrete trajectory, say z0 all the way up to zn, then there are many ways of constructing the next term, the sequence. Which, of course, I would denote by zn plus 1. Okay, so one common approach is to look at just the first, or at least the most recent n terms. So one common approach is to consider the sort of L previous terms. So this would be Zn minus L plus 1 all the way up to Zn. Okay, and as well as their derivatives. At those points. So this just comes from evaluating the vector field. Okay, so you have z dot n minus L plus 1 all the way up to z dot n, where z dot I is just f evaluated at zi. Okay. All right. So then if you have this, then one way of constructing this method is called a linear multi-step method. So we have a linear multi-step method. So this is a linear recurrence relationship. Okay, so the linear recurrence relationship is just some linear relationship involving linear combinations of both the z's as well as the z dots. So let's just write this in the following way. The sum is from I equals to n minus L plus 1 to n plus 1. Okay. All right, and then the plus 1, n plus 1 is there because in principle you want to use this to extract information about the solutions at the previous times. So z n minus L plus 1 all the way up to zn in order to construct zn plus 1. So zn plus 1 has to be in this relationship as well so that you can solve for it. So this is, of course, one way to think about these methods. But for now, it's like we're going to put this aside and we're going to consider what are called one-step methods. Okay, so we will first consider one-step methods. Okay, so what that means is that you have Cn plus 1 equals to some map which depends on the time step h and the solution at the current time Zn. Okay, so this mapping is generally nonlinear. And will depend on the vector field and or its derivatives. Okay. So if it doesn't depend at all, it's like on f of its derivatives, then you are not going to be able to get a method which does a reasonable job of approximating the solutions of the differential equation. Okay. All right. So these sort of one-step methods generate a mapping of phase space okay, so there's natural correspondence with the flow map. Okay. All right. So let's now talk a little bit about how one might derive one of these one-step methods, as well as some examples of these one-step methods. Okay, so you can of course construct one-step methods in many ways. Let me just describe some of them. So one-step methods can be derived or can be constructed in various ways. So one way is to appeal to the fundamental theorem of calculus. So if you apply the fundamental theorem of calculus, to a differential equation, say dz dt is equal to f of z, then what you get is the following, that the solution at t plus h, right, minus the solution at time t is given by the integral from 0 to h of f evaluated along a trajectory z t plus tau d tau. Okay, so basically what happens is that if you happen to know the solution of the differential equation going from z at t to z at t plus h, and you evaluated the vector field f along that curve, then the integral of that is going to be exactly the difference between the solution at the new time and the solution at the old time. Okay, so of course you can't really compute this directly because the right-hand side requires you to know the solution of the differential equation to begin with. So what you do, of course, is that you try to approximate this. So where you approximate the right-hand side using what is called numerical quadrature. so it's an example of that that says that, say, z at t plus h is approximately z at t plus some weighted combination, h times the sum of bi's f evaluated at z plus, z at t plus tau I, and this is sum from I equals 1 to s. So s is the number of quadrature points. So you have quadrature weights, which are the bi's, and quadrature points. Let's call that tau I. Okay. All right. So so with that in mind, let's look at a few examples of such methods which fit into this framework. So the simplest example is probably the explicit Euler method. Okay, so this says that the solution at the new time is equal to the solution at the old time plus h times the vector field evaluated at the old time. Okay, so of course this is what you get if you would replace the integral by the interval, the length of the interval, which is h, times f evaluated at the left endpoint, which is z at, or f at zn. Okay, so that's what you have there. The second example is what is called implicit Euler. And it's very similar, except that now the vector field is evaluated at the right endpoint, so zn plus 1. Okay, so this is again what you get when you replace the integral by evaluating the integrand at right-hand sort of right endpoint multiplied by the length of the interval. The third possibility is sort of a trapezoidal rule. And as the name implies, this is what you would obtain if you were to use the trapezoidal approximation of the integral. So this is zn plus 1 is equal to zn plus the average of the integrands at the two endpoints. Okay, again multiplied by the length of the interval. Okay, so that's what you get. And then finally, you have what is called the implicit midpoint. Method, which is what you get when you use the midpoint rule, which is what you get when you evaluate the integrand. It's like at the midpoint of the 2 points. So this would be h over 2 f evaluated at zn plus 1 over 2. Okay, all right. So, so if you are paying attention, it's like you'll see that there's this implicit versus explicit. It's like on some of these. So you might ask, well, what does that mean? So if you look at the first method, which is the explicit Euler method, you see that the right-hand side only depends on things you already know. You know the solution at the current times, which is Zn. You know the vector field evaluated at that point. So you can evaluate everything on the right-hand side in order to get the solution at the new time. Okay. In contrast, if you look at all the other methods, the solution at the new time, which is Zn plus 1, which is your unknown, shows up on both the left and right-hand sides in all these examples. So as a consequence of that, you can't just evaluate the right-hand side. You don't have enough information to evaluate the right-hand side. And you have, in principle, to solve a system of equations in order to figure out what z n plus 1 is. So one advantage, if you will, it's like of these equations are that they're in the form of what is called a fixed point equation. So you're looking for Zn plus 1 such that some transformation applied to Zn plus 1 is Zn plus 1. Okay, so you're looking for a fixed point or some sort of nonlinear map. And the advantage of doing things like that is that you can do what is called fixed point iterations. So you can just repeatedly apply the right-hand side until it essentially converges. So the advantage of this is that you don't have to use something like a Newton-type method, which involves essentially computing the Jacobian of the nonlinear equation, which in general is expensive to do. So oftentimes fixed point iterations are cheaper to implement. So in any case, these last three methods are all implicit because in principle you have to solve some sort of nonlinear equation in order to use them.